In our last lecture video, we have discussed about the oxidation using K-manophore, and we finished the discussion on that part, that is oxidation using K-manophore, and we found that for terminal alkynes like 1-butene, we will get two kind of products. One is carboxylic acid, another one is carbon dioxide. But in case of internal alkynes like this one and this one, there will be two kind of products or two kind of acids. First, their anions will be generated, anions of those acids will be generated, and in the last step, we will get different kind of carboxylic acids. Today, we will start with batch reduction of alkynes. This is nothing but a simple reduction method, and alkynes are selectively converted into transalkenes. So alkyne can be selectively converted to the trans. There is a possibility to form both kind of alkenes like cis and trans, but cis alkenes are less stable compared to the trans alkene. Since trans alkene is um, more stable, so this is the major product. So as a product, we will get the transalkene after the reduction. Now in this reduction, actually a solution of sodium or lithium in liquid ammonia is used, and the mixture of these two contains stoichiometric amount of an alcohol like ethanol. Okay, so as in the case of this batch reduction of aromatic system, the first step of this reaction is one electron transfer. One electron transfer to the antibonding pi orbitals of this alkyne. Okay, and which eventually yields a radical. Okay, let us look at this part. First, one electron is transferred from sodium to the alkyne into the pi bonding orbital of alkyne, and it generates a radical anion. And in the next step, the protonation of this radical anion uh, produces a vinylic radical. So this, after protonation, will produce this vinylic radical, which followed by transfer of another electron to this radical, this vinylic radical, from the sodium metal. And for that we will get a carbon ion, where both the R group in trans position. And in the last step, it again protonated from the ammonia solution by taking one hydrogen from ammonia, and it produces a transalkene. Next reaction which we will talk about is the addition of hydrogen, or we can say hydrogenation of alkyne to produce cis-alkene. In the previous reaction, that was also a reduction or the addition of hydrogen, which produces transalkene. But in case of this one, if we use a Lindlar catalyst, we will get cis-alkene. This reaction already we have discussed in the alkene when we are discussing about the alkene preparation mainly. So using Lindlar catalyst and hydrogen, alkyne will produce cis alkene, and here the addition is syn addition, and it will not further reduce to any alkane. And the reason behind the transformation of an alkyne to cis alkene, because the hydrogenation mainly continue or occurred on the surface of metal catalyst, of the metal which is used as a catalyst. Okay. Now for the mechanism, you can go through the alkene preparation part. There we have already discussed in details about the mechanism. Next reaction which we will talk about is the addition of halo acids to the alkynes. Halo acid means HX, which may be HCl, HBr, or HI, etc. And the reaction is actually takes place according to Markovnikov's rule. Okay, so in this reaction, the first step, addition of hydrogen halides to alkene. If we use one equivalent of halo acid, then what will happen? Now here is the example where we are showing that in the first step, when one equivalent HCl is added, it produces alkynyl chloride or vinyl chloride, and it goes through the Markovnikov rule. It follows the Markovnikov rule, and it's called the Markovnikov addition with a regioselectivity. And the chlorine actually goes into the highly substituted carbon. This carbon is more substituted than this carbon, because there is only hydrogen substitution, and here is a one R substitution. So this is a most substituted carbon where chlorine goes. The negative part of the halo acid enter. And if we use another second equivalent of HCl or any halo acid, then what will happen? Then we will get a geminal dichloride. Okay, so again the chlorine will go into the highly substituted carbon atom, and hydrogen will go into the less substituted carbon atoms, and we will get this kind of geminal dichloride. Let us look at the mechanism, what is going on actually. In the mechanism, we will find that the reaction goes through a carbocation formation. In the first step is the protonation of the alkyne with HCl in such a manner so as to give the most substituted carbocation. This one. What I have said, কি বললাম যে ফার্স্ট স্টেপটা হচ্ছে প্রোটনেশন অফ অ্যালকাইন উইথ দ্য রিঅ্যাকশন অফ HCl, এবং এই রিঅ্যাকশনে মোস্ট সাবস্টিটিউটেড কার্বোকাটায়নটা তৈরি হবে, because most substituted carbocation is highly stable, right? And after the formation of carbocation, the Cl minus will attack this carbocation, and it will form a bond with carbon, which will eventually give us the alkynyl chloride, right? In the next step, the carbocation is attacked by the chlorine atom, which I have told you already, and form the alkynyl chloride. Now, if we add the second equivalent, the same steps will be repeated again. In this case, this alkynyl chloride will be protonated using this HCl, and hydrogen will form a bond with carbon, and a carbocation will be formed. After this formation of carbocation, chloride will react with this carbocation to form a CCl bond, and we will get a geminal dichloride. Now the same reaction can be happened with the other halo acid like HBr and also HI, and in some cases HF can react with the alkynes. The next reaction is the polymerization of alkynes. Alkynes can undergo polymerization yielding different type of polymeric compounds under different conditions. Mainly there are two types of polymerization, linear polymerization and cyclic polymerization. This is example of cyclic polymerization where three molecules of acetylene under this condition produces benzene, and it's shown here again. Thus this bond is opened up and form a C-C bond. Similarly here also a bond open up to form a carbon-carbon bond, and here also. So it gives the benzene molecule. Another example is where instead of 3 acetylene, if we use a 4 acetylene, then we will, in presence of this catalyst, we will get cyclooctatetraene. Here is an example of the use of uh, propyne as a starting material, and if we use 3 molecular propyne, we will get 135 trimethylbenzene, that is the mesitylene. So polymerization have another kind of polymerization, that is linear polymerization, or alkyne may undergo another kind of linear polymerization in which the alkyne molecule, especially here the ethyne, that is the acetylene, combine to form products which have linear structure. Like here, two molecules of acetylene combine to produce first the monovinyl acetylene, which again react with another molecule of acetylene to produce diphenyl acetylene. Now this vinyl acetylene or the divinyl acetylene or this monovinyl acetylene may react with HCl to form 2 chloro uh, 2 chloro 1,3 butadiene, 2 chloro 1,3 butadiene, or which is called chloroprene, and which on exposure to air polymerizes to this kind of polymers, which is called neoprene, or it is actually a synthetic rubber. Besides this, linear polymerization of ethyne also undergo to produce polyacetylene or the polyethylene, having the formula C2H2 whole N under a suitable conditions. So these are the examples of polymerizations of the alkyne molecule. This acetylene is the first member of the alkyne series, and this is the simplest one, and which is one of the major chemicals used in the industry. In the atmosphere of Jupiter, also acetylene molecules have been found to exist. The acetylene have several physical properties as well as chemical properties. For example, among the physical properties, acetylene is very light. It has very light odor. It is a colorless, soluble in water, soluble in acetone. It has boiling point 83 degrees centigrade and can be liquefied at 1 degree centigrade. Chemical properties, among chemical properties, uh, we can found that it has a burning property with a bright flame, and it explodes at about 15 atmosphere pressure. So these are simple properties which acetylene has, and being a first member, it's the simplest most alkyne. So that's all for today's lecture, and by this lecture we actually finished our discussion on the alkynes. and we finished our module number 1.